In this tutorial, I'm going to be using MENOTR to fit thermodynamic data with an equation shown here that has to be solved implicitly, or using implicit fitting. So in this specific case, we're fitting to a two-site non-identical model with a scalar amplitude term. So in this specific case, we have two different equilibrium constants, one with 1e to the 6th, and the second is 1e to the 3rd. So that was used in the simulation of the isotherm shown here, and with varying xt. And our micromolecule concentration was held constant at 1 micromolar. So now, if our goal is to fit these experimental data and see if we can extract out these known values for the amplitude and the two different equilibrium constants. So the first step to do in this process is to open up, to go to this tutorial 5. So tutorial 5 is where this Excel sheet is located. And now we want to go about fitting this data. So we're going to go into MENOTR, and we're going to take the implicit fitting folder and copy it into MATLAB. Rather, we're going to copy the implicit fitting folder and put it into our working folder, shown here. Okay, so now it's in our working directory. So we're going to copy that working directory into here. So this is tutorial 5, and now we're going to go into this implicit fitting folder. So now we need to open up the model simulator. Is the first step in this process. And now if we, as shown here, the only sections that we need to edit here are section 2. So here we're going to define our x bar equation. So you can see it over here. So here we have it typed in, amplitude times k1 times x free plus 2 times k1 times k2 times x free squared divided by so on and so forth. We need to define our micromolecule concentration, which we have as 1 micromolar. Shown below here, we're going to define our parameters. So we're going to have a amplitude term, we have a k1 and a k2, are shown here. Now, the next step, so first thing you do is define the parameters. Then we have a series of steps that we have to do for each of the parameters which are defined. So the first is to convert the number to a string. And suffice to say, all you have to do is shown through here. So you would just modify the code in the exact same way where you'd have an _s for each of the parameters in your model, and then type num to string and the parameter name. Then the next step is to just assign x bar equals this, calling this function here, and then you're going to type x bar, and then each of the parameters, amplitude, k1 and k2, the order here doesn't matter as long as it matches through here. So what I would do is define each of the parameters, k1, k1, amplitude, k1, k2, then do the exact same steps here, and then here, and then here. Where the only thing you're changing is the name of the parameter that you're fitting with. Well, this would change, and then these would need to change depending on the parameter you're working with. And that's all that needs to change for section 1 to accommodate your equation. So now to actually execute the fit itself, you just run step 1. This is inserting your data. So it's critically important, once again, that your first column is your independent variable, our second column is your dependent variable, and the third is your standard deviation measurements. So copy and paste that over. In step 2, now we're going to be editing sections 1 and 2 as shown at the top. So section 1 is, once again, your initial guesses. So I put an initial guess for the amplitude of 3. We have an upper bound value of 20 and a lower bound of 0.01. We have a k1 of 1e to the 3rd, an upper bound of 1e to the 8th and 100, then 1,000, 1e to the 8th, and 100 for the k2. So our initial guesses are both 1e to the 3rd, or 1,000, and our upper bounds are both 1e to the 8th, and our lower bounds are both 100. We then load in each of these parameters as shown here for the param vals, the upper bound and lower bound as shown here. then we clear them out because they've been loaded into these respective parameters. Then now in section 2, we're just defining which parameters are allowed to float in each of the cycles versus being held constant or not floating. So we're going to perform 3 generations within the first cycle. So this is just the genetic algorithm. We're going to allow each of the parameters to float, thus they're equal to 1. We're defining each of the parameters with an _c to dictate that we're describing the cycle matrix specifically. Then we have a parentheses 1 to indicate we're in the first cycle. And we're not going to perform non-linear squares in the first cycle, so that is equal to 0. In the second cycle, we have the code by default set up to, so this is the second cycle, so we have parentheses 2. We're going to perform 3 generations. Then we're in the second cycle, so parentheses 2 all throughout for each of the parameters, and all those are still allowed to float. Now the only modification is that we're now performing non-linear squares also. So now in the next step, we load in each of our connect parameters and non-linear squares as shown through here. And then since those are loaded in, we can now clear out those variables. So now we've edited both sections 1 and 2 as shown here. So the next step is just to run this code. So we run step 2, and we now has loaded in those parameters into the workspace as shown to the right here. And now all we have to do is simply run step 3. So as you can see, we're on the first period, the first optimization routine, the first cycle, and the first generation. And now we're going up to the generations, and the chi-square is going down. And now we're kicking over to the second cycle. So now we're using the non-linear squares also. And our fit is progressively getting better and describing the experimental data better and better. Okay, so you can see here that in the first period, while the chi-squares are quite similar, one of them is better than the other 3, as shown here with the relative standard deviation of the chi-square between the different optimization routines was 2%. So what occurred is the best set of parameters were used as the initial guesses for the second period that was carried out, as shown through here. Those parameters were optimized, and here now there was a small difference in the chi-squares. However, it's less than 1% difference, so thus the code stops and the fit is now complete. As you can see from the final plot, we can see that the best fit line describes the data extremely well, and the residuals are randomly distributed about 0, suggesting that we have a good quality fit. And now our fit parameters that we're able to extract out are shown here. Now if we copy these over, we can see that we got format cells. We got approximately 1 for the amplitude, which is correct. We got 1 e to the 6th for the first K1, and instead of 1 e to the 3rd, we got 0.9 e to the 3rd, which is very close. So as you can see by the best fit line, we're describing the data extremely well. And also in here, so we have our best fit parameters that are shown as our fit parameter values shown here in the workspace. We have a plot of the experimental data with the best fit line, and you can ascertain also those the best fit line shown here with the simulated data, where the first column is the independent variable and the second column is the dependent variable. So you have independent and dependent. And now in the event that you lose this information by clearing the workspace in CLC, you can retrieve it once again by just clicking over here to fit workspace, and it has all that information.